First, thank you for organizers who gave this very nice opportunity to come Jeju, the famous islands in Korea. Yeah. So I believe yesterday everybody enjoyed your trip. Yeah, in Ireland. Yeah. This talk is a joint work with Alastair Darby, which is still going on. Yeah. I will introduce the algebras from closed-oriented triangulated manifolds. This kind of algebras are different from the known algebra in topology, such as homotopy, co-homology and homology, K-theory and cobordism and bodism. Actually, basically the idea and the philosophy of this kind of algebras come from the new theory of so-called the cluster algebra. This kind of for the cluster algebra was introduced and defined around 2002 by some mathematicians, Fomin, Zalevinsky, and Bernstein. They constructed that algebra. Yeah. That algebra is originally come from the representation theory. Also, rather than the topology. Yeah. This cross algebra can be realized from the so many areas, such as quantum theory, algebraic geometry and number theory. So many areas. Here, we just use the idea and the philosophy of the cluster algebra to construct algebra from the closed orientable triangulated manifold. Our objective is just find the new PL invariant for PL manifold. Yeah, this is our objective. Yeah. So here is the outline of my talk. First, I will give some explanation. Maybe everybody is know that about triangulated manifold and the PL manifold, and then I will give a introduction about class algebra. Also, for this class algebra, the forming Shapiro and Thurston gave a realization from the topology of the surfaces. Yeah, I also introduced their work, and then I will show you how to define and construct algebra from the general case. But here, we just work in the case of the Basteller-Moore. Yeah. Unlike forming the Shapiro and certain work, they just consider the Moore, the Wamu. Yeah. Finally, I will show you some idea and results how to define PL invariant for PL manifold. Yeah. So here is a definition of the triangulated manifold. Yeah, which is the special simply so complex, whose geometric realization is a topological manifold. Yeah, this is the definition. What is the PL manifold? PL manifold is also a special, the triangulated manifold. Here some of the condition for every non-empty simplex. The link is the PL sphere. Yeah. Here, the PL sphere is triangulated sphere, which is the PL homomorphic to the boundary simplex. Yeah. For the PL homomorphism, given the two simply so complex, if you can do the subdivision for the two complex, finally you can get commutatorial equivalent for that. Then you can say that the two simply so complex are PL homomorphic. Yeah. That's its definition. Here is the remark. If the dimension is less than 4, yeah, there are the three categories: the smooth category, PL category, and the topological category. There's the three categories are same. Yeah. In the dimension 4, yeah, smooth category is equal to PL category. That means, yeah, for each PL full manifold, there are exactly one differential structure. So there also is an open problem about the four-dimensional sphere. Yeah, how many are there differential structure? But here you also can see how many are there PL structure as 4. Here is the definition of the best move. Boostable and the panel of the book. Give the more detail about that. Here the K is the triangulated manifold. If you want to do the best move, the first you need to find phase. This phase needs to satisfy some of the condition. The link is just the boundary of the missing phase. Here, the B, this phase is not in simply so triangulated manifold. This is just a restricted condition. If you want to do best move, then you can do that. The move you can write down B and A, around A. For this here, you need to move some parts and then union the new parts. In something you just do surgery on the triangulated manifold. Maybe I will show you the example of that. Maybe this one. Okay. For the dimension 2 case, here is A, A, this is the one phase, The link just 3, 4, If you want to do best move, here just some partial part of the triangulated surface. Yeah. The 3, 4, they should be not in K. Yeah. Then you can do the better move around this edge. This it just do the one move. You just move this part and then union the new part. Geometrically, you just move this edge and add this new edge. Yeah. In this case, 1, 2, this edge will be not in the new triangulated surface. 3, 4 will be, yeah, in the surface. Here the pair, yeah. If you want to do a better move, you need this pair, yeah. Here we call this pair the best pair, yeah. If the AB, this ordered pair is the best pair, this the ordered pair also is a better pair, but is not in originally triangulated manifold. It's just in here, yeah. So this one operation is just the inverse operation. Then if you do better move this one to here, you also can do inverse operation. Just go back and return to origin case. Yeah. This is just one move. Yeah. Also, yeah. If the A just 1, 2, 3. Yeah. Here the link is just empty. Empty means that you need the ghost vertex. Yeah. Ghost vertex. You also can do the better move, just the 0 move. That means you need the new vertex. Yeah. And gets this 0 move. You also can do the inverse, the operation, just 2 move. 2 move, yeah. If you do 2 move, you just move the one vertex, yeah. So yeah, here, yeah. If don't consider the restricted condition, this link, the 1, 2, just a boundary 3, 4. 3, 4 maybe is still in the surface. Also, you also can do the move, yeah, but that move is not best move, just the one move. Yeah. Here is the Panguna theorem, yeah, in 1987, yeah, which say that 2 pure manifolds are pure homomorphic if and only if the M1 can be transformed into M2 by a finite sequence of the best move. Yeah. But here, our purpose want to give a description about algebraic description about the best move. Yeah. But, yeah. Here it is a cluster algebra. Now I just show you some of the main features of cluster algebra, not precise definition. Yeah. Cluster algebra of rank n is the commutative ring with the units and the non-zero divisor, which are generated by a family generator called the cluster variables. Later I will show you some example about that. Here, the sets, all cluster variable is the non-disjoint union collection of the n subset. Here, the rank n, you need to consider the n subset. Each n subset is called the cluster. Cluster. There are the following the exchange property for the clusters. For any cluster and any variable in this cluster, you can find another cluster and elements in this new one, such that you just use the new one to replace to the older one. They change, and then there is an exchange relation for these two variables. Here M1 and M2 are two monomial without common divisors. Which are give in n-1 variable here. This definition is different ordinary definition for the known algebra. Something like first you choose a seed, and then you can do exchange the variable at any direction. You can go infinity. A little bit complicated. Here is just an example. Here A is the coordinate ring of this one. This is we can understand. Here elements, this one is just a matrix with this condition. Determinates. Just one. Now you can consider the AD as the cluster variable and the BC as the scalars. Then there exists just two classes, AD. So in this case, this algebra just generated by cluster variable AD, satisfying this condition. This condition is just exchange relation. Here, just an example of the rank 2. Here, rank 2, we need to use the two positive integers, u and v. Here, the cluster variable infinitely many elements. Satisfying this condition. This condition is just exchange relation. Each pair is just a cluster. You can do using this formula. You can get the other variable. The first, you can start with this pair. Using this formula, you can get this one. You can. So here, using this one, you can get arbitrary variable can be reduced to be in a rational function in x1, x2, using this one. So you can see this class algebra is just a sub-algebra generated by variable, which is inside of the field of the rational function generated by the two variables. Here is just a definition for general case. The first you need a semi-free. Maybe the semi-free definition. If you consider the positive, the real numbers, and consider the ordinary addition and multiplication, this is just a semi-field. For this multiplication, the forms group, then you can get the group ring. Here, F is just fields of the rational function in n indeterminates over this group ring. Then you can define the general case class algebra for general case of rank n. Here, each class which contains n elements, you also can say n subsets, is a collection of elements of this field. The n elements will be algebraic independent. This is a very number theory. Here, for each class, you can get the 2n tuple the elements. Here, this coefficient comes from this semi-free. For each the pair, the plus and the minus, satisfy this condition. Forming they call the condition normalization condition. For each class variable can be exchanged from the one class to form the new class around this way. Just replace the older one by new one. This xk and sk plan satisfy this. Exchange relation also. Here we also can give us more detail about this definition. It's the two monomials. There's an exponents can be encoded in some square integer matrix. Usually, this matrix is just square symmetric. The called exchange matrix. Here, this is the monomial, and the two monomial can be the writing as this form. Using this matrix. Here is the power. Then exchange relation can be written down by this way. This triple will be called a seed. Seed. Something like the plant, yeah, give a seed, can, yeah. Yeah, here the exchange between the class can be extended to the seed mutation, yeah. Here for the matrix, yeah, there's a matrix mutation, which is defined by this way. For this twin tuple, yeah, also we can say the coefficients, yeah, also can be uniquely uniquely determined by this normalization condition together with yeah, this one. Then you can define the class algebra of the rank n, which is defined as the sub-algebra of this field, yeah, generated by old class variable. Or this old class variable can be obtained from the initial class. You just fix the seed, yeah, initial class, and by iterating the seed in all the direction, yeah, you can get all the class variable, yeah. Here, the field can be regarded as the field of the all rational function in variable, just initial class, yeah. Here are some of the references. Yeah, the Fomin, Zelevinsky, and Berenstein. Yeah, they wrote a series of papers, which, yeah, established the theory of the class algebra. Yeah. I'm sorry, maybe. Yeah. I need yeah. Here, I need to give us some of the introduction about the work by Fomin, Shapiro, and Certain. Yeah, they construct a class algebra from the triangulated surface. Yeah, here as the orientable closed surface of the genus N. This one means the all triangulations of this surface. Here, the M is the fixed number of the vertices. Yeah, fixed number. Yeah. This result is very known. Yeah, for arbitrary the two triangulations, yeah, they are pure homomorphic. Yeah. Also, yeah, here you never change the number of the vertices. Yeah, if this one is pure homomorphic to this one, that means, yeah, it's equivalent to the statement. Yeah, this one K1 is obtained from K2 by a finite sequence of the better only one moves. Yeah.
Excuse me. Is there a similar result for general dimension?
No. Yeah, it's just in the three-dimensional case. Yeah, there are some results. If you fix the number of the vertices, yeah, the arbitrary triangulation for the sum given the three closed manifolds, you can change for arbitrary two triangulation can be changed each other by only 1 and 2 better move. Yeah, but the higher dimensional there are no similar result. Yeah. Yeah. Here is the work. Yeah. Now we take triangulation. Yeah, K. Yeah. Then this is very easy to calculate. Yeah, the number of the edge. Yeah. How to construct the class algebra from this triangulation? Yeah. Here we will see that the class algebra is of rank this one. Yeah. So OH will form as a class 1 class. Yeah. Here this means just the set of the all edges. Yeah. Give a edge, you can define the variable. Yeah. You can get a class. Yeah. And then all the class variable can be produced from this inertia class. Yeah. Here some of the steps about definition, construction of the class algebra from the triangulated surface. Yeah. The first, the form the matrix. Yeah, square matrix. Here, triangle is just a two-phase. For arbitrary, the first you need to define for each triangle. You define the matrix. Yeah, because here the surface is orientable. Yeah, then you can define this matrix. Yeah. Yes. And then this one just the sum of all the this kind of the matrix. Yeah. You also now n is just the number of the edges. Yeah, you can label all the edge by this n colors. Yeah. Then you can write down this matrix by this way. Yeah. Here, then you can consider the matrix mutation. Yeah, at the direction k. Yeah. This mutation is just an involution. Yeah. You also can do the inverse operation. Also, this matrix just corresponds to the Wamu geometrically. Yeah. This is just the Iceberg. Yeah. So then you can get the algebra from inertia C. Yeah. Here the theorem. Yeah, by the three mathematics. Yeah. If the K prime is obtained from K, but one move here just one move, maybe not better move. Yeah. Then you can do the matrix mutation, and then you can get the class algebra which are isomorphic. Yeah. So here, there are one-to-one correspondence between the matrix mutation and the Wamu. But here, the Wamu just without any restricted condition. Yeah, there are no one-to-one corresponding to this mutation between the better Wamu. Actually, yeah. For example, this one is just the boundary of the 3 simplex. Yeah, 3 simplex. In that case, you cannot do any better Wamu. Here, 1, 2, 3, 4. Yeah. This edge, the link of this edge, just the boundary of the 3, 4. But the 3, 4 is still in here, yeah. But you also can do Wamu around this edge. You can get this one. And then you also can do the Wamu around this one. Around this one, yeah, you just get this one. Forming and superior and certain cause this kind of the triangulation, the ideal triangulation. Yeah, it's not the real symmetries complex. Yeah, just a cell decomposition. Yeah. Yeah. How much time? Yeah, maybe it's 5 minutes. Yeah, maybe I need to. Yeah, here for the higher dimensional case. Yeah, a little bit different 2-dimensional case. Also, we need to ask some questions. Yeah, here this one just the sets all closed-oriented triangulated manifold. Yeah, given triangulated manifolds. Yeah, we need to do how to choose class variable, how to define the exchange matrix, how to define the matrix mutation which corresponds to the beta mu. Yeah, how to define the exchange relation around the seeds. Yeah. But here we'll choose the n-1 simplexes as the class variables. Yeah, something like the 2-dimensional case. The reason is depends on the following. Yeah, if you do the beta mu, yeah, you just change the local part. You can easily calculate the f vector and something. Yeah, you can get this one. Yeah. Then yeah. For if you want to define the exchange matrix, yeah, here is a little bit complicated. Here, assume this triangulated manifold is some complex. Yeah. This the number the vertices m. Yeah. Here you need to consider the lexicographic ordering. Yeah. For this one, this the natural. Yeah. This one means the oriented simplex. This one is the simplex with the inverse orientation. Yeah. Here you also can give the canonical orientation. Yeah, for the each simplex. Here, yeah, around this. Yeah. In general case, we need this generalized formula. Yeah, if the if the k the equal 1, we know that there is the boundary operators. Yeah, the k the one time you just choose the k element. Yeah. Then we also need to define the pair ordering for each simplex. You can consider the all the H faces, and you need to give the pair ordering for each pair. In all here a little bit. In this for this definition, we need this formula. Here is the example. This is just a two-dimensional case. If you consider the higher dimensional case, here you need to use this formula. Here there's some of the convention. I think maybe it's not enough to haven't not enough time to But here some maybe I just give us some outlines. Here. Like the two-dimensional case, we also can define this exchange matrix. And if we do the better move, we need to know the matrix mutation. For this one, we also need to give an analysis for the local structure about bistellar pair. Pair. Here some of the local structure. Then if we do the better move, we can choose the permutation. Here we just consider the middle dimensional better move. In that case, this permutation gave a commutatorial equivalence between the local path. Local path. Here, the local path. This one and this one, something like this. And then we can define the matrix mutation. We also can, but here we need permutation. There are so many permutations satisfy this equation. Here, if you choose the different permutation, maybe you give a different mutation. Here, about the exchanges relation for seeds. For that case, we need here just subsets. Each one is obtained from the K by doing a finite sequence of the better H move. You can define the better exchange graph, using the triangulated manifold as vertices, and better pair defines the age. For example, for this one, there are the 10 elements and 30 better pair. Then you can get this graph. This graph gives us all the information about how to change the one triangulation to another one. Here, then we can define the better class. Here also, different two-dimensional. Now, in classical class algebra, one time you just change one variable, but in our case, one time maybe change not only one variable, maybe more than one variable, yeah. Also, yeah, sorry, yeah. Defines, yeah, the seed, yeah. Here also can define the best seed mutation, yeah. This is exchange relation, yeah. A little bit, yeah, complicated. Here, if the H is equal 1, just two-dimensional case, there are only one exchange relation. If the H is more than 1, there are so many exchange relations. Also, yeah, this one. And then, yeah, we can define the best class algebra, yeah. Also, return this example, yeah. Our algebra is computable, yeah. For that's, yeah, I'm sorry, yeah. For this example, we can calculate, yeah, what is the algebra, yeah. Finally, you can calculate this algebra is just the quotient algebra of some polynomial algebra with some ideal, yeah. Then we also can get this one. If the two closed-oriented triangulated manifold satisfy this condition, yeah, their corresponding algebras are isomorphic, yeah. For the PL invariant, yeah, here just consider all the PL manifolds, yeah. Choosing a PL manifold, you can get subsets. Here, each one is PL homomorphic to given PL manifold. The idea using this set to define algebra, yeah. Here, also just consider the even dimensional case. The idea using this one define direct set. And we can obtain the direct system, yeah. Finally, you can define limits, yeah. Here, yeah, you can define the binary relation, and in this case, yeah, we can show that this one forms a direct system. Certainly, yeah, we think, yeah, this lemma should be true for arbitrary, and yeah. Also, yeah, for this case, this one form a direct system, yeah, and then we can define the limit. Finally, in this case, this algebra is a PL invariant, yeah. In other words, if the two manifold are PL homomorphic, then their corresponding algebras are isomorphic, yeah. So, yeah, thank you, yeah.